recording. Great, so we start off with nuclear physics and radioactivity. Sounds like a bunch of fun, doesn't it? So in this first half, we're going to take a look at the nuclear physics aspect, which is going to be kind of a review of chemistry probably. But physicists always look at things from slightly different angles than chemistry does. They're always trying to make stuff and we're always trying to understand stuff. So maybe that's why we have a different point of view. And then in the second half, that's when we'll talk about the radioactivity part, featuring one of my favorite physicists, Marie Curie. So we're going to focus on just the structure and properties of the nucleus and binding energy tonight. And then we're going to go and take a look at radioactivity in the second half. And there are a bunch of really interesting applications of this. The main application that we're going to focus on is half-life and radioactive dating. So we start off by taking a look at the basic aspect of the nucleus. Nucleus, protons and neutrons, of course. Protons have mass and positive charge. Neutrons don't have charge, or do they? And that's how come the words are carefully chosen. The neutron is electrically neutral. Now, when I was much younger, I used to think that, like a proton, because it's got mass and charge, kind of has something extra. But if you look carefully at these two numbers, there's a really important distinction between them. So let's follow my mouse. The distinction between them is that, it's in the details, right? So 67262, 67493. So actually, the neutron has a slightly larger mass. So it's the neutron that actually has something extra that the proton doesn't, and that'll be revealed in a few minutes. It should bother you that neutrons and protons can live in a nucleus that has a diameter on the order of 10 to the minus 15 meters, because we thought that these positive charges would all repel each other, and I think we've made that point several times. So what's the deal? What's happening? If you're trying to count who's who, then this is another way we'll take a look at nuclear notation tonight, and that's really similar to what's shown in Appendix B. So Appendix B is going to look at different elements, and it's going to present the mass number and the atomic number. So the number of neutrons and protons have to be integers, but then it becomes a little confusing why the atomic mass is definitely never an integer. So Appendix B provides a nice summary of things for us. So when we take a look at different elements, that there are several different isotopes that are possible. So an isotope means that, well, the number of protons is sort of like a social security number that identifies what that element is. But the mass number could be different for different isotopes, because sometimes in the example for helium, that has 2 protons, but it might have in some isotopes 3 neutrons, in some other situations 2 neutrons. So the masses don't all have to be the same, and that's what Appendix B reveals to us, is that we get a sense about what the relative abundance is of that particular material. So helium-4, that's the one that's the most abundant. Helium-3 is actually of great interest to people who study fusion, and it occurs naturally in seawater, but it's not that abundant, as we can see. Most of the helium that we have is helium-4. And that's how we refer to isotopes. We talk about the element, and then we refer to the mass number to identify what kind of isotope we're talking about. So a reminder about Rutherford's experiment, and trying to find out, that's how we do particle physics, is that we throw stuff at other stuff and see what happens. So by throwing helium nuclei at a very thin foil of gold, the surprising result was that most of the elements, most of the alpha particles, the helium nuclei, just went straight through and weren't deflected at all. But once in a very great while, we'd see some kind of deflection happen. So the helium particles are positively charged, and the conclusion for this is that um, the atom must be mostly empty space if all these particles just go right through and they're not deflected. But every once in a while, we see a really strong deflection, and so the positive charges must be in a really small spot. So that's a bit of a historical review. Now, before we go further, just want to talk about units. This is really helpful. So this is SI units, of course, the atomic mass unit, and as we've defined it. But also, this is a really handy unit too, because it tells us what the energy is that's associated with that mass. Now, we jumped over the relativity chapter a little bit, but E equals mc squared is, I'm sure, something that you're familiar with, and it's called mass energy equivalence. That mass and energy are really two different sides of the same coin, and you can convert energy to mass and you can also convert mass to energy, but it's something very difficult for humans to do, but stars seem to do it all the time with relative ease. So now let's take a look at, we've talked about units, then let's take a look at the relative mass of the building blocks for all elements. And again, I pointed out to the small difference between the mass of a neutron and the mass of a proton. A helium atom, helium-1, just has one proton and no neutrons. But still, the masses are a little bit different, and the reason for that is, well, hey, let's take a look at these two numbers. If you add these two numbers together, you get the mass number for a hydrogen atom. Okay. So we want to take a look at this idea about mass defect. And a good question is that if we have a stable atom that's in a bound state, and in that bound state, it's going to, if you're trying to break up the atom, if you're trying to break up the band, so to speak, it's going to take a lot of energy. And we can actually calculate out exactly how much energy that's going to take. So the example that's shown here is for carbon-14. So if we take carbon-14 and 6 protons and 8 neutrons, then we can use the numbers that were shown in the previous slide to calculate how much of the mass is represented by the protons and how much of the mass is representing the neutrons, and then add them up. The electrons, well, the electrons don't make a very significant contribution in terms of the binding energy of the nucleus. So that's they're kind of a wash. Now, if we go and take a look, so this sort of says before and after. What before really means is that we take all the parts and add up the mass of those parts. But then after, we go take a look at Appendix B, and we're looking for the exact mass of carbon-14. So we go off to Appendix B, take a look at carbon. Carbon's got lots of isotopes. Carbon-12 is the most common, but carbon-14 is the one that we use to determine the date of some organic materials, because its half-life is around, well, something like 6,000 years. So this can be pretty useful in determining how old a piece of organic material is. So we're not talking about something that's been fossilized. We're talking about, some Neanderthal cut a branch off a tree to make a club, and then got, absentmindedly left it in a cave. And then some years later, a scientist is stumbling around the cave, and they're like, hey, this club looks like it was made by a Neanderthal. And then they use carbon dating to figure out how old it is. So, but we'll talk about exactly what that mechanism looks like. But but I digress. Carbon 14, 14.003242. Now I'm going to go back and take a look at our notes. And I put in that number, and you can see there's a small difference. This is the mass of the part. This is the mass of the whole. And there's a little mass missing. So if we take the difference between the two, we find out that the missing mass is on the order of 1/10 of an atomic unit, which if we multiply by that conversion factor that we saw back here, multiply by 931.5, then we get this. This is how much mass, but this is how much energy that mass represents, right? Missing mass, what happened to the mass? It got converted into energy. And it's a negative number, meaning that if you're going to try and break up this carbon 14, that you're going to have to provide enough energy. And you can see this as MeVs per c squared. That's handy because this is an m still, it's a unit of mass. But if you want to do E equals mc squared, you'd multiply by c squared, right? So then it means that the energy it takes, the binding energy, the energy it takes to break this up is going to be 102 MeVs. All right, so let's try one really quick. And if you have access to that mass defect calculator, that's great. But let's go ahead and just try one really quick. So I'm going to go to Appendix B. Let's find, let's see. Michael, can you unmute yourself? I have a question to ask you.
Yes.
What is your favorite element?
Magnesium.
Okay. And so let's just take a minute and write down this for magnesium. And any reason, any reasons why you chose magnesium?
Not really. I had to work with it a long time ago, and then it just stuck with me, I guess.
Okay, magnesium 24. I had, during my day job, we hired 2 science teachers this year, and that was one of the interview questions: is what's your favorite element and why? And they were chemistry teachers, so it was legit.
I hope they had better answers than me.
No, not. Yeah, no, a lot of people would just, you know, because it's sort of, you're supposed to embellish on it, you know, at least that's the idea. And a lot of people go, yeah, carbon bonds with a lot of stuff. Okay. So anyway, I'm going to write down the mass number. And so that's 23, and we really do need all these digits. So 23.985042. Okay. And that's magnesium, and its atomic number is 12. Okay, sounds great. Going to go to the mass defect calculator so you can see this. And we know that magnesium, its atomic number is 12, so we're going to type in 12 here. And its mass number is 24, so that means the number of neutrons is 12. And the electrons, I guess we could put it, yeah, let's put it in the electrons. So same as the number of protons, so that's 12. And then the actual mass number is 23.985042. Right, so we have a small difference, and that means that there's some mass missing. That's where we get the name mass defect. And when we can convert that mass number to energy, and then that's the binding energy for the element magnesium. How are we doing on that concept? Does that sound good? Joanne is nodding her head. Alexis,
Good.
nodding her head. Yay. Okay, good. Michael, good job with the class participation.
Thank you.
So anyway, here's just a blank slide about how to do that. Now let's get into the juicy stuff. And I don't have a clock. Can I get a check-in? How much time do we have left? Can you see it on your screen?
Are you going for the half hour or the hour?
No, there should be a countdown
Oh, I've never
on,
noticed that
on the
before.
recording.
No, I think it only starts the last 5 minutes.
Thank you. So I've got more than 5 minutes.
Cool.
All right. Now, because this is something I really wanted to talk about. First of all, I mentioned this a little bit. This is an energy level diagram. We talked about this a little bit when we were looking at the hydrogen atom in chapter 27. So anything, this is this is representing force between the neutrons, or nucleons rather. And the blue line is what we would see if we were doing just Coulomb's law, because the neutrons can fit together just fine, but the protons, they really are always trying to get away from each other. So this shows that the force, because it's a 1/r² force, it's going to blow up as we get to very small numbers. So what we see that happens differently is that, well, obviously nuclei can exist, and they do exist, and they have multiple positive charges on them. So it's a different force that takes over. It's a short range force. It's interesting. And out of the four fundamental forces in the universe, gravity, electromagnetism, strong nuclear force, and weak nuclear force, I mentioned before that Einstein worked really hard to try and unite all those things into grand unification theory and never was able to do it successfully. So this is still kind of a mystery. What happens when you bring two protons together? Well, you bring in the first proton for free, and then you bring in the second one, and you want to take the first one and just kind of, put a little glue on it so it stays in place. Then you bring the second one in, and a little magic happens. Now, at this point right here, if you can see where my mouse is, that there would be a really strong repulsion here. And if I let go of the positive charge, it's going to rocket and head out the other way. But once I get close enough, if I am able to exert enough force, once I get close enough, then the strong nuclear force takes over, and it's very, very strong. Shocking. Yeah, physicists not really creative in the naming things, but anyway, it kicks in, and you can bring in another positive charge, and it's going to fall in here, but it leaves the big question about how much room is actually available for additional nucleons. 10 minutes. There we go. Okay, now I can see the clock too, so don't worry about reminding me. But that sounds just about right. So how many nucleons can you stick in here? We know that you can bring the neutrons in here, and as soon as the neutrons get in kind of close, they too get sucked in by the strong nuclear force. So how many can you get in there? Well, this is part of the idea about what nuclei are stable and which ones are not. So this gives us a binding energy per nucleon, and it increases as these elements increase in complexity. And we get up here, and iron has the strongest binding energy per nucleon. That means it's the most stable element. But as you keep on throwing stuff on top of it, then we wind up getting to a point where they're just unstable, because again, there is not enough room for them. So this region gets saturated with nucleons. Neutrons can sort of dilute the Coulomb repulsion force a little bit, but as the as the nucleus grows in size and it starts approaching, as it gets bigger and bigger, then the outer parts might be too far away to be subject to the strong nuclear force, and the atom might fall apart. All right, so we know iron is the most stable nucleus, and in the process of fusion, our sun right now is turning hydrogen into helium on the outside, and through the process of fusion, it's turning helium into other stuff. And as you get closer and closer to the center of the sun, we see fusion of much heavier elements. That's why the term "you're all made of stardust" comes from. Because yeah, all the elements in your body were made in stars at some point, and stars that have since exploded and shed their constituent parts throughout the universe. But fusion stops at iron. So that's the current hypothesis, is that when our sun finally dies and collapses, it's just going to be a solid chunk of iron. Can't wait for that. All right, so what about this stability thing? In early numbers of protons with the lighter elements, we see it looks like a 1-to-1 mix is pretty good. So the big red line is neutrons equal protons. So the slope of that is 1. Now the reason why I see lots and lots of dots here is because those would represent isotopes. Each vertical line represents one element, but each of the dots themselves represent different isotopes, because then they would have a different number of neutrons. And so as we get to elements that have more protons, then the need for dilution by mixing in more neutrons becomes a little more important. I thought this was interesting because you might be curious about synthetic elements. So we're always making new ones, but they're not very stable, and so they don't really last very long. But this is an example about how a particle accelerator can actually synthesize more elements, and it happens by smashing two other elements together. And so if we take a look at conservation of numbers, that 117 is tennessine, and 97 plus 20 makes an atomic number 117, and then 249 plus 48 gives us 297. And then if you whack it with another 3 neutrons, then you get it up to 297, and that one seems to stick around a little bit longer, but not very long before, because it's just too big and it's going to fall apart. It's an example of how in this situation we're making nucleons or nuclei that are too big, and their outside parts fall outside the strength of the strong nuclear force, and they just fall apart. So I don't know if you really can call these official elements. I think some people are just trying to get their names on elements, personally, but okay. So that wraps up the beginning part, the first half of chapter 30, and then we'll start talking about radioactivity. Let's make a little bit of progress here since I have a little bit of time. And again, a huge favor. I have to fix this slide because I was looking it up, and I'm going to edit this right in front of you. First person to double Nobel. And Einstein actually only has one. She shared the first Nobel Prize with her husband. There, first person to double Nobel. Way to go. And she's such an amazing person, so I thought I'd throw a little bit of biography information in there. And so Pierre was actually killed in a car accident. She later on died at age 66 from complications of exposure to radiation. And she kind of knew that that was going to happen, but they worked really hard on trying to do early work with safety, because they knew this is something that had to be contained somehow. But one surprising thing, when I was doing a little bit of digging, I didn't realize this, but she, in World War I, actually would go out in trucks on the battlefield and use small X-ray machines to help diagnose soldiers and their treatment. So I thought that was super cool. All right. Well, I'm just gonna, we'll probably review this, but I am just gonna go a few more deeper here. So in terms of the radioactivity, we're gonna talk about, there are 3 different kinds, and these are early names that were given to them, but now we know them to be different particles. So the early names were alpha, beta, and gamma, because they had different properties. So there's radiation. How do you detect radiation in the first place? Well, Marie and Pierre Curie were noticing that photographic film was getting exposed even though it didn't come out of the can. And so photographic film was one of the ways that they used to try. The film looked kind of fogged when it got developed. So that was one of the ways that they were detecting radiation. Alpha particles turn out to be helium atoms stripped of their electrons, and so they have a charge of +2. And beta particles turned out to be electrons, so they have an atomic number of -1. And 0 is used here because essentially they have very little mass compared to protons and neutrons. And then gamma radiation, well, that turns out to be high intensity photons. So they are way deep in the electromagnetic spectrum. So lots and lots of energy. Very, very short wavelengths, very high frequency. All right, and I think that's a good place to stop. So we just got a little bit in there, and we're going to stop recording here. And I'll just ask really quickly, is there any questions that people have? All right, well, cool. I'm going to post a quiz 27 probably tomorrow morning. I mean, yeah, quiz 27 tomorrow morning. And then there's only one more. Whoa. Okay. Have a great weekend, everybody.
Thank you. You too.
Hi, Pluto.
Many thanks.
Thank you.
Thank you.
All right. Hey, man, pay attention. What are you looking at? You're supposed to look at the camera. There we go.
Pluto, do you want to meet my cat real quickly?
Oh, yeah. Look. Whoa. That cat looks bigger than Pluto.
She definitely is. All right, thank you.
All right. Have a good night. Have a nice weekend.
Thank you.
Bye.